And just a couple more examples just to get some experience more than anything else. So part 4 of section 7.5. This is example 10. So in a survey of 1,000 eligible voters selected at random, it was found that 80 had a college degree. Additionally, it was found that 80% of those who had a college degree voted in the last presidential election, whereas 55% of the people who did not have a college degree voted in the last presidential election. Assuming that the poll is representative of all eligible voters, find the probability that an eligible voter selected at random, and then there's a bunch of questions. So in order to get a handle on this, I'm going to make a tree. So the first branching in general is the first piece of information they gave me, which talks about having a college degree. So we're going to say a degree and then the complement of that. We know that 80 out of 1,000 had a college degree. So 80 divided by 1,000 is 0.08. Yes, 0.08. That would mean that the other 920 out of the 1,000 did not have a college degree. So that would be 0.92. So again, that's 920 out of 1,000. This is the 8 out of 1,000. I'm going to say add to 1. And then the second piece of information is whether or not they voted in the last election or not. So my next branching is going to be voted or the complement. Voted or the complement. So voted or not, voted or not. 80% of those who had a degree voted in the last election. So this would be 0.8. This would be 0.2 because they have to add to 1. Whereas 55% of those who did not have a degree voted. So 0.55, and that makes this 0.45. And there's our complete tree. Now we can answer some questions. So again, the question's asking us, find the probability that an eligible voter selected at random, A, had a college degree and voted. So the probability that they had a degree, and because it says and, I know I'm looking for the intersection, voted. So degree, voted. So we're just going to multiply these two together. So that would be 0.08 times 0.8, which gives us 0.64. And again, this is that and as the intersection. So, okay, part B says, let's find a probability that an eligible voter selected at random did not have a degree and did not vote. So the probability that they did not have a degree, that's degree complement, and did not vote would be vote complement. So that's down here. So that's 0.92 times 0.45. Which gives us 0.414. Okay, part C is asking voted in the last presidential election. So now they're not designating whether or not you have a degree. They just want to know whether or not you voted. Well, that's two branchings. Anything that has B on the end. So we're going to multiply across and then add down. So we're going to take 0.08 times 0.8. So the probability that you voted, 0.08 times 0.8 plus, now we're going to put 0.92 times 0.55. 0.92, 0.55, kind of squished in there, but okay, and if you do that, you end up with overall 0.57. Okay, and then they want to know what's the probability that you did not vote in the last election. So I could do the same thing. I could multiply across the vote complement and add them together, or because those are the only two branches that are left, I can do the complement. So 1 minus the probability that you voted would be the probability that you did not vote. So 1 minus 0.57 is going to give us 0.43. I can only do that because that's the remaining branches they're asking for. If they were asking for just one of those, I would have to multiply across to get it. So. Okay, and finally, our last example for section 7.5, number 11. Number 11 says, an assembly line has 3 inspectors. The probability that the first inspector will miss a defective item is 0.05. If it passes the first inspector, then the probability the second inspector misses it is 0.05 also. If the defective item passes the first 2 inspectors, the probability that the third inspector will miss it is 0.0001. What's the probability that a defective item is missed by all 3 inspectors? Okay, we're going to assume that these are independent. So in other words, if inspector 1 misses it or does not miss it, doesn't impact inspector 2 at all. So I'm not going to draw the complete tree, but this is what's going on. So basically, here's our first inspector, and they are either going to miss it or not. But then looking at the second inspector, and he's either going to miss it or not. Or we're going to look at the third inspector, and he's either going to miss it or not. So what we're looking for is this branch times this branch times this branch. Well, they told me that the probability the first one misses it is 0.05. Second one misses it is the same, and the third one missing is 0.0001. So then the probability that they all miss is simply going to be the 0.05 multiplied by the next branching of 0.05 times their last branching of 0.0001. And if you multiply that all out, you're going to get 0.00000025, or 2.5 times 10 to the negative 7. Pretty tiny that defective part is going to make it through all 3 inspectors. And that wraps up section 7.5. I hope you've enjoyed making those trees. They're a great way to organize your thoughts when you're doing probabilities.